Hello. We are going to look at the following problem. Evaluate the integral of 1 over 2 plus cosine theta d theta, and we will find out that to solve this problem, it's handy to know about the substitution z equals tangent of theta over 2. That will change this integral, which involves a fraction with sines and cosines in it in general, to something that is an integral of a function of z dz, where that function of z is a rational function which we can apply partial fractions to if necessary. Let's consider the integral of 1 over 2 plus the cosine of theta d theta. We want to evaluate this integral. The usual substitutions that you might think of will not work in this particular integral, but it turns out that the following substitution, z equals the tangent of theta over 2, does simplify this to something that we can somewhat easily evaluate. So let's start with this substitution, and let's change the integral to an integral of a function of z times dz. So if we start with z equals tangent of theta, then dz is going to equal secant squared of theta over 2 times the derivative with respect to theta of theta over 2. So that tells us then that dz is equal to 1/2 the secant squared of theta over 2 times d theta. I left off the d theta up here, but let's go ahead and put it back in. So that's dz. If we look at the integral 1 over 2 plus cosine theta d theta, we need to figure out what the cosine of theta is equal to. So let's work on that, the cosine of theta. Well, we're using a half angle in z equals tangent theta over 2, so let's try the cosine of theta over 2 plus theta over 2, just using the fact that theta over 2 plus theta over 2 is equal to theta. If we use the addition formula for the cosine, this will give us cosine squared of theta over 2 minus sine squared of theta over 2. Now, let's take that cosine squared minus sine squared and divide and multiply by the cosine squared of theta over 2. So we can write the cosine of theta as the cosine squared of theta over 2 divided by the cosine squared of theta over 2 minus sine squared of theta over 2 divided by cosine squared of theta over 2, and this whole thing then multiplied by the cosine squared of theta over 2. So the cosine of theta is equal to 1 minus the tangent squared of theta over 2 times the cosine squared of theta over 2. And so the cosine of theta is equal to 1 minus the tangent squared of theta over 2. And the cosine square theta over 2 term we can write as 1 over the secant squared of theta over 2. Now, let's remember that we have the trig identity sine square u plus cosine square u equals 1. And if we divide that by cosine square u, we would get so the cosine of theta can be written as 1 minus the tangent squared of theta over 2. And then secant squared of theta over 2 is 1 plus the tangent squared of theta over 2, another trig identity. So I'll write this as 1 over 1 plus the tangent squared of theta over 2. But let's remember that z equals the tangent of theta over 2. And so we can write this as 1 minus z squared times 1 over 1 plus z squared. And so we get the cosine of theta is equal to the fraction 1 minus z squared over 1 plus z squared. This is an important formula that we will need when we're evaluating, let's recall, the integral of 1 over 2 plus cosine theta d theta. Now, what about the sine of theta? Let's see what we can do with that. So now we're going to look at the sine of theta. We want to get this also in terms of. So let's write this as the sine of 2 times theta over 2. We can use also, instead of this, just the sine of theta over 2 plus theta over 2 to get sine of 2 times theta over 2. So using the addition formula for the sine, or just realizing that we have a double angle formula that comes from that, and hopefully remember what that is, this is equal to 2 sine of theta over 2 times the cosine of theta over 2. So let's write the sine of theta the following way. We're going to multiply and divide that last equation by the cosine squared of theta over 2. So we'll write it as 2 sine theta over 2 cosine theta over 2 divided by cosine squared of theta over 2 times the cosine squared of theta over 2. So let's rewrite this the following way. If we do this division here, we can write that fraction as 2 times the sine of theta over 2 times, or divided by, the cosine of theta over 2. And cosine squared of theta over 2 is 1 over the secant squared of theta over 2. And so we get 2 tangent of theta over 2 times 1 over secant squared of theta over 2 is the same as 1 over 1 plus the tangent squared of theta over 2. We should have a secant here, put in a c. And so the sine of theta is equal to 2z times 1 over 1 plus z squared. 2 tangent of theta over 2 is 2z, and the fraction 1 divided by 1 plus tangent squared theta over 2 is 1 over 1 plus z squared. And so we can rewrite this then as just the single fraction 2z over 1 plus z squared. So we now have a formula for the sine of theta. We do not need it in the integral that we're doing presently, the integral of 1 over 2 plus cosine theta d theta. But if we needed to evaluate an integral that involved a sine of theta, this might come in handy. Now let's remember that we need to get dz. And so far what we had was that dz is equal to 1/2 secant squared theta times d theta. Okay? And if we look at this for a minute, we can rewrite this as dz equals 1/2 times 1 plus tangent squared, this should have been a theta over 2 here, tangent squared of theta over 2 times d theta, and this is 1/2 1 plus z squared times d theta, remembering that we're making the substitution z equals tangent of theta over 2. And so we can solve this for d theta, and we get that it's 2 divided by 1 plus z squared dz. So now when we consider the integral of 1 over 2 plus cosine theta d theta, we have the following. We have the integral of 1 over 2 plus, and then the cosine of theta was 1 minus z squared over 1 plus z squared. And then d theta was 2 over 1 plus z squared dz. Let's see, we need a brace right here. Now, multiplying the denominators together, we can simplify that integral to the integral of 2 divided by 2 times 1 plus z squared plus, still in the denominator, 1 minus z squared dz. And this can be simplified a little bit further using a little bit of algebra to what? Well, the numerator is going to be 2, and the denominator. If we look at the denominator, 2 times 1 plus z squared is equal to 2 plus 2z squared. And when you add 1 minus z squared to that, what do we have? We have, let's see, a 2 plus 1, which is a 3. And we have a 2z squared minus z squared, and that adds up to plus z squared dz. So we now have a fairly simple integral to handle. Let's remember that the integral of 1 over 1 plus u squared du is equal to the inverse tangent of u plus a constant. We can use this formula to evaluate the integral that we are facing. So, the integral of 2 over 3 plus z squared dz, we can write as 2/3 the integral of 1 over 1 plus z squared over 3 dz, and that we can write as 2/3 the integral of 1 over 1 plus z over the square root of 3 quantity squared dz. And we look at that and we'll make a substitution. U equals z over the square root of 3. And in that case, du is going to be 1 over square root of 3 dz. So these are the two substitutions that we'll make. So the integral that we're looking at is 2/3 the integral of 1 over 1 plus u squared in this case, and the dz is going to be the square root of 3 times du. It comes from this formula right here, multiplying both sides by the square root of 3. The square root of 3 du equals dz. So the integral that we have, we can rewrite as 2/3 the times the square root of 3 integral of 1 over 1 plus u squared du, and that can be written as 2 square root of 3 over 3 inverse tangent of u plus a constant of integration. But then u, remember, is z over the square root of 3. So we get 2 square root of 3 over 3 inverse tangent of z over the square root of 3 plus a constant of integration. But now remember what z is. Z is the tangent of theta over 2. So recalling that, we have 2 square root of 3 over 3 inverse tangent of 1 over the square root of 3 tangent of theta over 2, and then plus a constant. So basically we have an inverse tangent of something involving a tangent of theta over 2. And this is the solution. This is the integral of 1 over 2 plus cosine theta times d theta. So we have evaluated that integral using the substitution that z equals tangent of theta over 2. So how did we evaluate the integral of 1 over 2 plus cosine theta d theta? We made a trig substitution. Z equals tangent of theta over 2. From that, we were able to show that d theta was 2 over 1 plus z squared times dz. Cosine of theta was 1 minus z squared divided by 1 plus z squared. Sine of theta turned out to be 2z divided by 1 plus z squared. That transforms this integral into an integral of the form r of z dz, where r is a rational function of z, a polynomial in z divided by a polynomial in z. In general, these can be evaluated by using partial fractions. Integrals of rational functions we saw before are often evaluated by a partial fraction decomposition. I hope you enjoyed this lecture, and there should be more following. Good day. You probably noticed that in the solution to evaluating the integral of 1 over 2 plus cosine theta d theta, the solution turned out to be rather long and cumbersome, kind of messy too, I guess. But that's life. Not every problem has short solutions. I picked this particular problem because the solution is comparatively short to some others in the same category. If we tried this technique, this particular substitution, on this more complicated integral that we see here, we would probably find it to be extremely messy, and it would take a long time using, say, partial fractions to decompose it into a series of simpler integrals to evaluate and then resubstitute back to get your answer in terms of trig functions involving theta. In that case, I would probably decide to use computer software to evaluate this integral, something like, say, Maple or Sage Math, rather than to try to do this one, solve this problem by hand. So how did we evaluate the integral of 1 over 2 plus cosine theta d theta? We made a trig substitution. Z equals tangent of theta over 2. From that, we were able to show that d theta was 2 over 1 plus z squared times dz. Cosine of theta was 1 minus z squared divided by 1 plus z squared. Sine of theta turned out to be 2z divided by 1 plus z squared. That transforms this integral into an integral of the form r of x, r of z dz, where r is a rational function of z, a polynomial in z divided by a polynomial in z. In general, these can be evaluated by using partial fractions. Integrals of rational functions we saw before are often evaluated by a partial fraction decomposition. I hope you enjoyed this lecture, and there should be more following. Good day. Thanks for watching this video. I hope you have found it to be an enjoyable learning experience, a substitution that many people don't see these days in a calculus course. As time progresses, I hope that this series of videos will also cover many more topics from calculus, so please stay tuned.